we're live. It's great to have you, Konstantinos, speaking about QNLP implementations. The stage is all yours.
Thanks, Robin. So yeah, I'm going to talk about QNLP implementations on NISC devices. I'm Konstantinos. This is work done with Alexis and Giovanni, and I want to say that we did this as part of the CQC team, which is starting in Oxford soon. And I'm sure there will be a lot of info about this on Slack by Bob. This is also, I mean, in summary, it's about making quantum computers speak. And since this is a quantum week of fun, I hope it's going to be fun, even though running stuff on these devices is not actually fun. So to get going, this is the outline of the talk. We start from word to sentence by Lambeck. And then we go to diagrams using graphical languages. And then we map these diagrams to NISC devices. It's as simple as that. And then we make up some NLP tasks and see the performance. So I'm going to take you through this nice story. And I want to stress that this is what I'm going to present is a scaled up version of the experiment that we presented last year in December on QNLP20 with Alexis and Giovanni. So, okay, yes, remark also that everything I've done from implementation to drawing to applying functors, and I'm gonna show you what these things mean. I did it with DisCoCat, which is the Python library that Alex and Giovanni wrote. So just to begin from the basics, and I'm sure there will be some high overlap with Stefano's talk that you saw like an hour ago. But let me take you through the basics again. So we define the pre-group grammar in which words are composed to make sentences. And words are basically states in a process theory, and they are given types. So a state is something with no output or no input, and output is a bunch of types. Types are called basic types or atomic types, and they come with an integer on them, decorating them, this kind of integer. And this is what is called the pre-group adjoint order, but all you need to know is that the grammatical reductions are generated by cups, these wires here, and they join types who have an adjoint order that increases by 1 to the right. So if this is abstract nonsense, let me take you through an example and you'll understand what I mean. So Walter, who loves dude, bowls. So a noun gets type n to the 0, a relative pronoun gets this product of types of some n's with some adjoint orders 1 or 0 and s to the -1 here. A transitive verb accepts a noun to the left and a noun to the right, has a sentence type here. And so you see, if I have an n to the 0, I can join it with an n to the 1 because its adjoint order increases by 1 to the right. So I put a cup on it. So this nested pattern of cups is the grammatical reduction, and the words compose to form a whole sentence. So this is what the pre-group grammar model tells us, and a pre-group diagram just represents the grammatical reduction of such a sentence. And we call a grammatical sentence anything that has only one dangling wire, which is an s to the 0 wire. And then what Bob and Mernouche and Steven did in 2010 was create the DisCoCat model, where they said, okay, we have these diagrams. We have the pre-group grammar. We draw them as diagrams, the grammatical reductions of a sentence, where we have the compositional structure, where words compose to make sentences. So what if we fill the words with distributional meanings? So we combine distributionality of meaning with compositionality of grammar. And then they created this distributional compositional categorical model of meaning called DisCoCat that we're going to be basing the whole framework on. And then what Will and Bob did, well, they said, well, yes, we have this tensor network model of language if we're working in real vector spaces, but what if we try to construct these tensor networks on a quantum computer? And they have a paper, a very nice paper, which is the first QNLP paper that uses DisCoCat, and under the assumption of a quantum RAM, where you can load distributional data onto the tensors. You can do stuff like, well, see, for example, this sentence needs a loves Greek tragedy, and you can see which class, as in which concept it belongs to, which category it has the highest overlap with, sports, art, politics, and so on. So they obtain a quadratic speedup by doing so, by importing a quantum algorithm for the closest vector problem by Nathan Wiebe and other people. So what we do is take a Nisky approach, like Stefano described in his talk, and basically what we do is we give substance to the states. A state is prepared. We make a functor that maps the states in pregroups to circuits that prepare states, quantum states, on a given number of qubits from the all zero state. So the pregroup types that are assigned to the words get mapped to number of qubits. Every type gets a specific number of qubits, and then this uniquely defines the space in which a quantum state that encodes the meaning of a word is embedded. Correspondingly, the cups that make up the grammatical reductions get mapped to the Bell effects. In the example where we have the wire carrying 1 qubit, it's just a C note with some post-selection on plus and 0. So it's just a maximally entangled effect. And this generalizes for any number of dimension for the wire, which is a power of 2. And now, specifically the circuits that prepare states, they are composed of universal gate sets. So we can choose the C naught, some Euler decomposition for a single qubit state, Hadamard's, control Zs with phases on them. So choosing a universal gate set, we make ansatz for these words. And a specific choice of ansatz could be like an IQP style ansatz, where I have alternating layers of Hadamards and control Z rotations. And a D depth layer would be something that has D stacks of these alternating Hadamard and control Z layers. So the total set of parameters which define such an ansatz is what defines the word state that is prepared by this circuit. And having all of this equipment together, and with specific choice of hyperparameters, like I said before, qubit number is assigned to every type. We decide what ansatz is given to every word depending on how many qubits is defined on, and we choose an IQP depth T. Having that stuff, and also making the choice that a relative pronoun, for example, can be modeled as what is called a Frobenius ansatz, which is something you can find here. But basically what it means for the qubit case is that we fix it to be a JZ state prepared on whatever many number of qubits is dictated by the types that we assign on the pregroup types. So for example, because I said too many words, let's go to see some pictures. The circuit for Walter who loves dude, who gets these spiders, which are JZ states when we map them to qubits. And then if I take them through this functor that maps states to circuits and cups to Bell post selections, then I will obtain such a circuit. So this is Walter, this is who, this is loves, this is dude, and this is bowls, where you see I've set for words that are defined on 1 qubit an Euler decomposition like this one, and words that are defined on 2 qubits that like loves, I've set at depth 2 IQP ansatz. And then because this circuit looks weird, then we just put it in normal form. But here, when I say weird, I just mean that it reflects the sentence structure. So the grammar is obvious here. Here we just make it look like a nice actual quantum circuit. And you see that everything is prepared from the all zeros and everything is post-selected to the all zeros. And all we have to do is just run these circuits. So in running these circuits, we define, like we want to achieve something by running the circuits. Let me go back and stress that I've set the quantum wire to carry no qubits at all. So the diagram you see has no open wires. So that means that the sentence meaning is encoded in a scalar. This is a scalar. It's just a number. And because it's a 0 to 0 transition, its probability is going to be, you know, some some unitaries here, and then all zeros. And then if we take the amplitude squared, which is what the quantum device is going to actually give us, then this is going to be a scalar between 0 and 1, right? So what we can do with this, what can we do with this? Then we define a binary classification task, which is, I'm going to, in more detail, define what we did last year in December. What we do is, given a bunch of sentences along with binary truth labels for them in diagrammatic form, we go and say that if we take them through the functor that prepares circuits, we end up with circuits with truth labels on them. So now that we have the circuits, this, we call it our corpus. This is our corpus, and it's labeled corpus. So we have a bunch of circuits and binary labels on them. Then what we do is we split the corpus into training and test set. So let's say half sentences here and half sentences here. So we're going to train the parameters on the words so that this cost function is minimized. And this cost function, what is it? Every circuit evaluated, I said, returns a scalar. And we're going to interpret the scalar to be its approximate truth value. So it's going to be something between 0 and 1. And if it's below 0.5, I say it's 0. And if it's above 0.5, I say it's 1. So the cost function, minimizing this cost function, is going to train the parameters of the words so that when the circuits are evaluated, the correct labels in the training test are reproduced. And I want to note that correlations between sentences arise just from the fact that words participate in multiple sentences. Otherwise, the task would be impossible to train. So we minimize the cost function. It's like training or learning the functor. And then by doing so, we will recover theta star, which is the optimal parameter values. And then by evaluating these circuits, we will recover the predicted labels, which are the optimal ones. So after training, these are the predicted labels from the circuits. So we can quantify the training and test error by the Hamming distance, average Hamming distance. This is the Hamming distance of the rounded predicted values, because I said they are between 0 and 1, so I can make them 0 or 1, and I see their Hamming distance from the actual labels of the corpus. And this is the error. Like if I get them all correct, it's 0. And if I test on the rest of the sentences I haven't trained on, and I get them all correct, then I've done excellently. So this is a schematic of how the learning works. The diagrams are made into circuits. The circuits go into the IBM device. IBM device spits out the predicted labels. They go into my laptop. The laptop spits out the cost function. Well, if I'm happy, then I spit out the optimal labels. If the cost function is not low enough, then I update the parameters with some optimizer. Here we use SPSA because it's a noisy landscape from the quantum computer, and SPSA seems to work well also in other publications I've seen in quantum machine learning. So after the update, we loop around. We create the new circuits with the new parameters, and we loop around until convergence, and we get the training and test error. So let me show you classical results where first, before we go to the quantum stuff. So first, let's make a vocabulary like this, where I have two nouns, two transitive verbs, two intransitive verbs, and the relative pronoun, which gets the GAZ ansatz, remember? And I make 30 sentences, and I label them by hand so that the truth labels are consistent, because I've seen the movie. And I keep 15 for the training and 15 for test. And then we get this. So over 20 realizations per IQP depth, we see the cost function reaching a lower minimum. So the more depth I give to the IQP ansatz, the better the task works. This is where I give the noun space 2 qubits, and this is what I give the noun space 1 qubit. So in both cases, increasing the IQP depth means better performance, but of course it means more iterations for SPSA for it to converge. And this is in the inset is the training error and the cost and the testing error. So the black is kind of not so nice, but if I use a different optimizer like Bayesian hopping, which is a global optimizer, over local optimizations, where in the local optimizations I use Nedler-Mead, we see a clear downward trend in the error, both in testing and training. So the red, I mean. So this is encouraging. It's an open question whether Bayesian hopping or whatever other global optimization is realistic for NIST devices, but at least for the classical, it's fine. And so now that we've seen that the task is possible and it works and it's well defined with classical simulation, then I can go ahead for the implementation on NIST devices. And these are the 3 devices that I used through the CQC contract with IBM: Montreal, Toronto, and Manhattan. They all have quantum volume 32, and Manhattan is quite big, but the circuits I run are not crazy big, so it doesn't matter which one I use. Actually, Montreal was my favorite. And to compile the circuits onto the actual device, I used CQC's ticket compiler through the Python package PyTicket. I took the leap of faith, and actually trust my quantum compiler to do the compilation and minimize the depth and make the circuits fit into these constrained architectures shown here by these connectivity graphs. And here is the example of the compilation of the sentence I showed you before. Walter, who loves dude, bowls. This is the circuit we created with DiscoPy. And this is what Ticket made it look like on an IBM device on Montreal. These are the ticket passes that I used that were recommended to me by the ticket team from CQC. And they seem to be working fine. And to show you the actual results from the actual quantum computer, where the circuits were evaluated on the quantum device instead of classical, like I showed you before, I start with a very ridiculously small corpus of 6 sentences, where 5 of them become test, and only one of them train, and one of them I use for test. And I use 1 qubit for noun space and 2 qubits, IQP depth 2. And after only 5 SPSA iterations, I achieve like perfect performance. Okay, fine, it's very small, but at least it's it works. It's something as almost as small as what we showed last year. This is a 5-parameter thing. Last year we showed 2 parameters only, so it's still very small. It's not so impressive. Then I choose a bigger corpus made of this, from this vocabulary, and it's 16 sentences, and these are 8 sentences for training and 8 sentences for testing. And what I get is this, with different choices of hyperparameters like number of nouns and number of qubits for noun space and IQP depth, and unary words, as in words that are defined on 1 qubit. What ansatz should they get, RZ or Euler? Well, the training is on this number of parameters respectively, but this diagram is not so pretty, right? It's not very clear what's going on. Note that SPSA iterations are only 30, so we either get disappointed or we continue. We think that classical is better than quantum, or we just we are stubborn and we continue, and we say, well, at least if they are stocks, then at least they're going down. So if I'm shorting them, I'm happy. Maybe just focus on these 2 that seem to be doing a bit better. So these are where I have 1 qubit for nouns and IQP depth 2. Let's fix these hyperparameters and try harder. Try harder means more SPSA iterations, nothing fancier. And indeed, we converge to something not abysmal. So training error is quite low, like 12%. Testing error is quite not so good, like it's 50%, but I'm sure we can do better by using regularization techniques and maybe global optimization. I'm sure if I let it run for a week with Bayesian hopping on top of the SPSA, I can and I can make this drop like I did before in my classical simulation. So Guy Sensei is proud of you for trying harder. And I wanna make a remark actually, that something I found weird, but then I was told by QML people, actually Chris Self, who is in the Slack channel roaming around, that this thing, I thought this is weird, but then, so if you minimize on a quantum computer, you get the parameters, and then you try these parameters on the circuits. By evaluating the circuits on a classical computer, you will get wrong labels sometimes. And I was puzzled by this, but apparently it's fine because, you know, the noise on the quantum computer is shifting the landscape so that the parameters on after optimization on the quantum device, the noisy one, means something else in that context. So when I change my context and try to run a noiseless classical simulation, then of course I'm going to get different results. I don't expect this to be the case if I were running stuff on a fault-tolerant, error-corrected quantum computer. But hey, noise is you know, dirty. So these are the results I wanted to show. I want to stress that I want to remark again that DisCoCat is quite NISQ friendly. So I don't think that I know of another NLP setup which is so friendly for application on NISQ, specifically quantum devices. Anything else starts relying on quantum RAM and you know, applying Grover or SVDs and other stuff. But I mean, DisCoCat allows us to run these very small experiments. Okay, it's binary classification. I didn't write you know, Shakespeare with a quantum computer, but at least we can actually run stuff today with the noisy machines that we have. And I think that's quite cool. So for the future, we can, you know, keep scaling up, playing with optimizers. We can see what Ricci and Stefano did with Bigraph, if it helps their compiler. There's also another thing called snake removal that Alexis and Giovanni did, which is another sort of way to reshape circuits, and maybe this helps for mixed states, where we don't do everything in pure quantum mechanics, but we use mixed states and channels. We can also you know, try to see what regularization techniques are there for quantum machine learning with parameterized quantum circuits, because I don't think this is a very explored area, regularization. And then, of course, yeah, Robin is looking at making other tasks more NISQ friendly, like sentence similarity concept classification, like Will Zhang and Bob Kuke did in their first QNLP paper with DisCoCat. We can try to parse, to couple the parser with the DisCo model, because as it is now, we are assigning the pre-group types by hand. And actually, the sentences that I generated, these random sentences that I generated from the vocabulary, were generated by context-free grammar. I'm using some routine that Giovanni wrote with DiscoPy. Actually, this is needed. Coupling parsers with the model is needed if you want to go to real-world data. And I'm sure we will have a very interesting talk by Vincent and Bob later on new grammar models. So I want to see what this means regarding QNLP applications on these devices, or even long-term devices, you know, assuming fault tolerance and stuff. I think this is all I wanted to say, and thank you.
Thanks a lot, Konstantinos, for your talk. The 25 minutes are already over, but I think there has just been coming a question from Stefano, as follows.
Yeah.
How do you check you're not overfitting on your small examples? What does generalization look like as you increase corpus size, number of qubits, and depth of ansatz? Did you hear that clearly, Konstantinos?
Yeah, I got the. It's a very good question, and it's the reason that I mentioned regularization. So Of course, there is always the danger of overfitting. So having a test error like this doesn't mean anything if I don't scale and if I don't actually introduce more new sentences. But this is the reason I mentioned regularization. I mean, if I don't actually look into regularization seriously, then I don't think I can actually answer this question in a satisfying way. Also, another caveat is that the whole universe is the amount of sentences that I choose. I mean, this is kind of a cheating way to answer the question. So when I say this is my corpus, I mean this is all there is in the universe. So I can try to generate more sentences and see what happens, but these are just preliminary results. I'm sure that with the right regularization, I can make it work.
Thank you for answering this. I'm sure there will be time on Slack to discuss that further.
Mm-hmm.
Seeing that as there are no further questions, maybe we just call an end here. So thanks again for the excellent talk, Konstantinos.
Thank you, Robin, for organizing and arranging.
You're welcome. See you later, everyone.
Thanks.